In this video, I want to look at defining both a prime ideal and a maximum ideal. Let's start with the prime ideal. Let's let J be an ideal of a commutative ring. Then we say J is a prime ideal if the product AB belongs to J implies that either A is in J or B is in J. So if the product is in there, at least one of the elements needs to be in that ideal. This would make it a prime ideal. In addition, we have that if J is a prime ideal of a commutative ring with unity, A, then A mod J is an integral domain. And I'm going to leave the proof of this up to you, but I highly encourage you to try to show that this A mod J is in fact an integral domain. Next, let's look at a maximal ideal. First, if J is an ideal of a ring A, then we say it's proper if that ideal is not equal to the entire ring, so if J is not equal to A. We then say a proper ideal J is a maximal ideal if there's no proper ideal K such that J is a subset of K and they're not equal. In other words, J is not contained in any strictly larger proper ideal. So any other ideals that contain my proper ideal J would have to be equal to the entire set. Let's let A be a commutative ring with unity. In this case, J is a maximal ideal if and only if A mod J is a field. So if J was a prime ideal, that meant A mod J was an integral domain, but if it's a maximal ideal, then A mod J is a field. And I am going to go through and prove this. The first thing I want to show, I know that A mod J is a ring, so I want to show it is a commutative ring with unity. Let's start with J plus A times J plus B. By definition, this is J plus AB. Since my ring is commutative, I know that's the same thing as J plus BA, which by definition is J plus B, J plus A. So it is commutative. We also need that there is a unity. And the unity element is going to be J plus 1, where 1 is the unity element of my ring. In this case, J plus A times J plus 1, this is J plus A times 1. And since 1 is my multiplicative identity, that's J plus A. So this is a commutative ring with unity. Now that I have this, in order to prove that A mod J is a field, we only need to show that if J plus A is any non-zero coset, then it has an inverse. So we just need to prove multiplicative inverses. Let's consider the coset J plus A. Since we want a non-zero element, we need the additional restriction that A does not belong to the set J. Let's let K be the set of all elements XA plus J, where X is in my ring A, and J belongs to my ideal capital J. And I won't prove it directly, but you can double check that K is in fact an ideal. In addition, my element A belongs to K since A is of the form 1 times A plus 0. In addition, every element little j of my ideal capital J is in K since J is equal to 0 times A plus J. Since all my elements J belong to K, then I know J is a subset of K. And I further know that J is not equal to K, since we also have an element A in that set, where A is not in J. However, we said J was a maximal ideal, so that set K has to be equal to my entire set A, my entire ring A. Since the entire ring A is equal to K, that means 1 belongs to K. So we can write 1 as XA plus J for some X in my set A and little j in my maximal ideal capital J. I'm going to rewrite this as 1 minus XA is equal to J, so 1 minus XA has to belong to my maximal ideal J. And since 1 minus xa belongs to j, that tells me j plus 1 is equal to j plus xa. Which is the same thing as j plus x, j plus a. So now I've shown that in A mod j, j plus x is the inverse of j plus a. So provided I did not start with the 0 element, I did find a multiplicative inverse, which is enough to give me that this would be a field. And I'm only going to prove this one direction. The converse proof essentially unravels this argument, and I suggest you try it out for yourself to show that if A mod j is a field, then j must be a maximal ideal.